In this video, we're going to state 3 stray theorems. 2 of them are rather trivial, but the third is quite important. So, starting simple theorem. Let V be a vector space, then V is a subspace of itself. And the proof then is going to be quite short. Certainly, V is a subset of itself. What else do we need then to be a subspace? Well, we need closure under addition, and we need closure under scalar multiplication, and we need a 0 vector to be in V. And all vector spaces have these properties. They are 3 of the 10 things that a set has to have to be a vector space. So V is a vector space. We have them, and we're done. Theorem. Almost as trivial as that. Let V be a vector space. Any vector space contains a 0 vector, and we are saying that the set containing only that vector is a subspace of V, called the trivial subspace. The proof of this, well, we need to be closed under addition. There's only 1 vector in this set, saying that we're closed under addition is the same as saying that 0 plus 0 equals 0, which is certainly true. And we need to be closed under scalar multiplication. Again, there's only 1 vector in this set. So what this closure means is that a scalar times the 0 vector has to be the 0 vector, which is true. And 3, We need the 0 vector to be in this set, which of course it is. The next theorem will be a little less trivial. Let V be a vector space containing some vectors v1, v2, up to vn. Our claim is that the span of these vectors is a subspace of V. Let's prove this just for simplicity. Let's only prove a special case where we've got the span of 2 vectors. The argument generalizes. If you have more, it just becomes uglier to write down. So it's a subset, first of all. V is a vector space. It's closed under scalar multiplication, and it's closed under addition. And the span is formed by taking scalar products and adding them together. So it's certainly a subset. Let's show that it's closed under addition. If something's in the span, it is a linear combination of those vectors. So let's take something that's in the span, and let's add something else that's also in the span, that's also a linear combination of vectors. And what we want is for this sum to be in the span, and it is. This sum is a linear combination of V1 and V2, so it's in the span of V1 and V2. And we want this to be closed under scalar multiplication. Take a vector in the span and multiply it by k. We are supposed to get a linear combination of these vectors, and we certainly do. Finally, 0 is supposed to be here. Is 0 a linear combination of V1 and V2? It certainly is. All of our conditions are satisfied, and this proof is complete.